Let me just extend the welcome of the organizers to all of you. We are happy to have you here at the more or less beginning of our program on kinetic theory. And let me just say a few words in general. Well, kinetic theory has really come a very long way, starting out from what Boltzmann did 150 years ago, 140 years ago. We have branched out into many, many new applications, in particular in the last, I would say, 10, 15 years. Kinetic theory has gone into, of course, nanotechnology, it has gone into biology, it has gone into sociology, and so on. And I think we really have an exciting time in front of us. And of course, as David already said, we're extremely happy that this time kinetic theory got, if I may say so, the first Fields Medal of its own. This time, the quotation of the Fields Medal for Cédric Villani was purely for kinetic theory. In particular, it was for two topics, and that is convergence to equilibrium of the Boltzmann equation. This was joint work with Laurent de Villette, who is here. No, he's not. He will come very soon, I suppose. And the other work is, of course, Landau damping, a joint work with Clément Moreau, who is actually now on the staff of the DPMMS in Cambridge. So we're really very happy that that kinetic theory has gained a lot of recognition, even from pure mathematicians and from pure mathematics in the last years. Yeah, so welcome to all of you. Let me just say one thing. There's actually three organizers for the program. That is, as David already said, Xijin, Jose, and myself. But I have to say that I consider myself an organizer in the weak sense, and maybe I can also speak for Xijin in the same way. And Jose is really carrying, I would say, the biggest part of the organizational load, and let me extend my particular thanks to this. Yeah, this is really all I wanted to say, and I pass the floor to Ansgar, who is one of the organizers of this meeting. Ansgar, please.
Okay, yeah, thank you for everybody for coming. Also welcome from me. My name is Ansgar Jüngel, and as Peter said, I'm one of the organizers, together with Jose Antonio again, and Peter Markovich and Xijin. Yes, maybe three small topics about organization. So one thing is that there's a small change in the program. So there will be a shift of the talk of Suganides, I think on Wednesday, with Thierry Goudon. So they just shift since Suganides maybe will come a bit later. But we will announce this again if we know more. Then for those of you who will stay longer here in the Newton Institute, there will be from next week on, there will be a weekly seminar on every Tuesday. So if you're interested in speaking, presenting your results, then please tell to Jose, I guess, if you would like to do so. Not this week, but from next week on. And the last thing is about preprints. So it would be nice if you are about finishing a preprint when staying here, you're working on some results that you mentioned the Newton Institute, and that you send your preprint to the preprint server of the Institute. So they're collecting preprints, will be also online. It would be nice if you could do that during your stay here. And moreover, if you have already finished preprints and their results you want to share with others, there's a box in the library where you can put your printed preprints in that box, available for everybody to see the newest results you have. Okay, perfect. Then I'm gone and we can start with mathematics. The first talk will be Francois Golse. And let me see. And Francois Golse from Paris will speak about homogenization of the linear Boltzmann equation in a periodic system of things.
Well, good morning, everybody, and thank you for the invitation to this nice conference. All right, so I will start with a topic which is kinetic theory, although and like what is mentioned in the title of the conference, I don't think it has much to do with biology or engineering. But anyway, so the motivation for this talk is that you can expect that homogenization of transport processes in a periodic system of scatterers or holes may lead to non-trivial mathematical phenomena because some memory of the correlations between obstacles and the trajectory, the particle paths, can remain after passing to the homogenization limit. And as we know, if you look at linear transport equation, or linear Boltzmann equation, a natural limit of the linear Boltzmann equation is the diffusion equation, is the heat equation, and these phenomena of having problems with the homogenization in periodic settings does not appear with diffusion processes, which lead to conceptually simpler results. So let me explain more about this. Okay, so I will start with the simpler situation, which is the homogenization of a diffusion equation in a periodic distribution of holes. Okay, so for simplicity, I'm going to look at a cubic lattice in the n-dimensional Euclidean space. So epsilon zn with mesh size epsilon, and the domain is going to be the Euclidean space Rn with both a radius r epsilon centered at lattice points removed. So in other words, it's the set of points, these omega epsilon r epsilon, which is the spatial domain for the equation, is going to be the set of points in Rn whose distance to the lattice points, to epsilon zn, is larger than r epsilon. On this perforated domain, you consider the Dirichlet problem with a known u epsilon, which is a function of x, scalar function of x. And so for simplicity, I'm going to take a Laplace equation minus Laplacian of u epsilon equals f, and I add a damping term to avoid spectral problems, say. Okay, so I look at this diffusion equation for which is posed in this perforated domain omega, and with Dirichlet boundary condition on the boundary of omega. And here, f is a data. It's a source term in L2 of Rn. Lambda is given. It's a positive number, and the unknown is u epsilon, as I said. Now, for this problem, there is a notion of critical size for the obstacles or for the holes, right? So there is a notion, given epsilon, there is a critical size r epsilon depending on epsilon. And this critical size, let me give it immediately. It's supposing that n is larger than 2. It's proportional to epsilon to some exponent, with that exponent being n over n minus 2. If n equals 2, there's an exponential, so forget about that. What do I mean by this being the critical size? Well, it's critical in the following sense. If the radius is asymptotically smaller than epsilon to the gamma critical, then you expect that the solution of this diffusion equation will converge to the solution of the same equation without the holes, right? So in other words, well, if the holes are too small in the limit, in the homogenization limit, you don't see them. On the contrary, if r epsilon is larger than epsilon to the gamma critical, so if the holes are too big, then what happens is that because of the Dirichlet boundary condition here, well, I mean, the boundary condition takes over on the equation, and eventually what you observe is that the solution u epsilon converges to 0 in the vanishing epsilon limit. And so what remains to understand is the critical case, r epsilon, where r epsilon is equivalent to epsilon to the gamma critical. Well, so that case has been investigated by many people. And I think I may miss some references. I think maybe the first one to look at that maybe was Ruslov in Ukraine in the late 70s. And I think there's I learned that result from Suranescu Murat, who published a paper in the 80s. And what these people proved is that if you take the critical size, say in dimension larger than 2, for each data in L2 of Rn, the solution of that Dirichlet problem here, so where you have the diffusion equation equals F in the perforated domain with Dirichlet boundary condition and the boundary of the domain, the boundary of the holes. So the solution U epsilon, which you extend by 0 inside the holes, converges in L2 to the solution of that same diffusion equation plus an extra absorption term. So in other words, the absorption parameter lambda is enhanced and involves an extra absorption term C, where C is a positive number, right, which is independent of the data. So everything remains linear here. All right. So several remarks are in order at this point. So you observe that the limiting problem in that case, it's still a diffusion equation. Well, the only thing that changes is that you add a lower order term, right? You had a 0 order term. So the limiting problem has the same structure as the original problem. It's set in the same phase space, if you want. You have the same number of variables to describe the problem. Now, another observation is that the coefficient C is found to be R times the capacity of the unit sphere, which is defined by this usual minimization problem. Okay. Now I explained these results in the case of the Laplace equation, but actually, or the Poisson equation. Actually, you can extend this result in the context of porous media. You can extend this result. It's been extended to the Stokes or even the Navier-Stokes equation, right? And the extension was done by Grégoire Allaire in the early 90s. And well, interestingly, if the radius is supercritical, then you observe you get the Darcy law of porous media, and the critical case epsilon to the gamma critical leads to this absorption term here, extra absorption term here, which in fluid mechanics goes by the name of Brinkmann's friction force in the Stokes equation, Stokes or Navier-Stokes. And at this point, there is really no difference. You can extend that result, the Allaire result, to randomly distributed holes at the same critical size. And this is a remark that we obtained with Laurent Devillette and Valeria Ricci a couple of years ago. So it's the same type of result. The only thing is that this extra coefficient C involves the empirical distribution of holes, but there's really nothing complicated in this extension. All right, so so much for the diffusion case. And let me turn to the case of the linear Boltzmann equation. All right, so the problem now is to homogenize the linear Boltzmann equation for a monokinetic population of particles. And you want to do that in a periodic system of absorbing obstacles. So absorbing obstacles is holes, which means that you have particles. When they reach the boundary of one of the obstacles, it's like a hole. They fall into the hole and they disappear forever, right? So they are absorbed. I'm going to look at specifically the two-dimensional problem. So here my domain omega epsilon is going to be the set of points in R2 in the Euclidean plane whose distance to the cubic lattice of mesh size epsilon is larger than epsilon squared, right? So what you have is if you want, it's a perforated domain, a billiard table, whatever you want to call it, where the mesh size is epsilon and the whole radius is epsilon squared. And then you let epsilon go to 0, and you want to understand the behavior of a linear Boltzmann equation in a domain like this with absorption boundary condition. Okay, so now let me start with an obvious remark. Here you see I'm considering the case where the distance between the scatters is epsilon, between the obstacles is epsilon, between the holes is epsilon, and the radius of the holes is epsilon squared. So it's going to be the critical size for the transfer equation, and it's not the same critical parameter. It's not the same critical exponent as for the Laplace equation. So here the critical exponent in every space dimension n, would be gamma critical equals to n over n minus 1, whereas in the diffusion case would be n over n minus 2. This is to do with the fact that here we have a first order PDE, so it's the scaling of the differential operator is not the same. Besides, I remind you that in a two-dimensional case, the critical exponent, there wouldn't be any critical exponent, the critical size would involve an exponential. It's not purely a power of epsilon. Okay, so here in this talk I'm going to consider only the two-dimensional problem. Most of what I'm going to take carries over to higher dimensions, but there is one thing that is specific in the two-dimensional case, which is a particular explicit computation that seems to be doable at the moment, only in space dimension 2. All right, so that particular computation has to do with the notion of free path length. So it has to do with, more appropriately, with the notion of mean free path. Okay, so let me explain that a little bit. I'm going to consider the free path length for free particles moving in my perforated domain, right? Forget about the collision process of the Boltzmann equation at the moment. So I'm looking at free particles moving in that domain. So the free path length, starting from a position x in the perforated domain omega, in the direction v, where v is a unit vector in R2. So this is what I denote henceforth tau epsilon of x and v, which is the first time where x plus tv hits the boundary of one of the holes. Right? So it's tau epsilon of x and v. Now, of course, this tau epsilon of x and v, it's a very complicated function. You see that that function oscillates a lot because it has to do with the quality of approximation of the. So if you're in space dimension 2, so your unit vector, it's a v1, v2, and say the behavior of this free path length has to do with the quality of rational approximation of v2 over v1. So suppose generically, if you pick v such that v2 over v1 is real, is irrational, then the behavior of tau epsilon has to do with the easiness with which you can approximate this ratio v2 over v1 by irrational, right? So it depends very much whether v2 over v1 is going to be algebraic number, transcendent number, things like that. So it oscillates a lot, and it's out of a question to understand the details of this function. However, what you can do is understand the distribution of its values, right? It oscillates a lot, so you can view it, if you want, as a random signal. And some time ago, Per Dahlqvist conjectured, and it's a paper that appeared in Nonlinearity in 1997, that you could find phi of t, which is the limit of the probability that tau epsilon be larger than t, and what I'm speaking as epsilon tends to 0, and what I'm speaking a probability that tau epsilon be larger than t, assuming that x and v are uniformly distributed in the omega epsilon times the unit sphere, right? So you want x and v, the starting point, independent and uniformly distributed, x in omega epsilon and v in the unit sphere. And Per Dahlqvist conjectured a formula for this, and Boca and Zaharescu proved 10 years thereafter that this explicit formula is correct. And then here is the explicit formula, right? So for each t, this phi of t, which is the limiting distribution of this probability here, is 6 over pi squared, so this integral from t to infinity of s minus t g of s. And g of s is this explicit function. Notice that this function is a constant for between 0 and 1. Now, if you look at the graph of this function, So phi is the blue curve. So it's a curve that decays slowly, decays like 1 over t at infinity, as t goes to infinity. What's interesting is that in the first part of the curve, well, interesting, what's surprising to the first part of the curve, this is really a parabola. The second derivative is a constant in that part of the curve. Anyway, so this function here, in the case of the transport equation, is what is going to replace the capacity and the enhanced absorption coefficient in the case of the diffusion problem. And let me explain this. Now, I'm going to need that function, and this function phi is specifically the thing which you can compute explicitly in space dimension 2, and that doesn't seem to be computable at the moment in space dimension higher than 2. All right, so now I'm considering the linear Boltzmann equation in the perforated domain omega epsilon. So here the unknown is going to be f epsilon of t, x, and v, so which is the particle distribution function. So you think you have a gas of particles, whatever they are, moving in that perforated domain omega epsilon. So this is the standard number density of particles which at time t are located at a position x with velocity v. And it evolves according to a linear Boltzmann equation here, written here. So dt f epsilon plus v del x f epsilon plus sigma f epsilon minus k f epsilon equals 0 in the perforated domain. So here I consider monokinetic population of particles. So the velocity is just a direction. Velocity, speed is 1 if you want. Here sigma is positive constant. It's the collision frequency. And k is an integral operator acting on the v variable only. And it's given by a symmetric kernel, symmetric collision kernel, which is a transition probability. So when you integrate with respect to any of the variables, you find 1. Okay. Now, so much for the equation. Together with that equation, you put the absorbing boundary condition, which is the equivalent of the Dirichlet boundary condition in the diffusion case. So the absorption condition here is that f epsilon of t, x, and v is equal to 0 whenever x is on the boundary of the domain, omega epsilon, and v dot nx is positive, meaning that nx is the outward unit normal on the boundary of the obstacles. So it means that no particle can actually leave an obstacle, right? And you prescribe some initial data, t equals to 0, which you can take as independent of epsilon. So now the problem that we want to study is, one, to find an equation for the limit of f epsilon as epsilon tends to 0, if you can find one, if it exists. I mean, to be able to describe the dynamics of the limit of f epsilon as epsilon tends to 0. And two, you see, because of the absorption, because of the holes, you're going to lose particles. So there's going to be a loss of mass in the system, right? And you would like to find the asymptotic mass loss rate. And especially, you would like to know whether it's exponential or not. Okay. Well, let me look at the first question. There is a first observation, which is kind of trivial, which is that in the limit as epsilon tends to 0, so I told you that the probability that tau epsilon is larger than t converges to some profile phi of t, but actually you can say a little more at almost no cost, which is that if you look at the indicator that tau epsilon be larger than t, this function converges to phi of t in L infinity weak star, right? So this thing is a periodic oscillating function, also oscillating in v, but the fact is that as epsilon tends to 0, this converges to its mean, right? So you don't see, the only thing that remains in the weak limit is the mean, right? Is the expectation. Although it's not a periodic function in v. In v, it's horrible, right? I mean, it's periodic in x, but it's nothing in v. Okay, so it's a little amplification of the result by Boca, Hazard, Escu, Dahlquist, and company. Anyway, so the answer to, I'm going to use this result, I'm going to need this result to be able to formulate the answer to question 1, namely the limiting behavior of the particle density. So what happens is this: in the limit as epsilon tends to 0, then the function f epsilon, the particle number density, will converge weakly to a function which I express as an integral over an extra variable s of capital F of t, s, x, and v ds. And I'm going to write an equation for the integrand. I'm going to write an equation for capital F, but at the moment, I don't know that I cannot write an equation or a PDE for the limit which is here, right? So the equation, without memory terms, if you want, a local equation, a Markovian equation, whatever you want to call it, I'm going to write under capital F. So here f, which is a function of tx and ts, x, and v, so you have an extra time variable, which I'm going to explain in a minute, satisfies for all for all position x and all velocity v in R2 process 1. So it's a prime where the holes have disappeared, right? It's the homogenized equation. So t and s are positive numbers. It satisfies the following equation. So here you have free transport dtf plus v del xf. There is a plus dsf, which I will explain in a moment, plays the role of an absorption term, which is the part of the absorption which is due to the holes. There is the original loss term in the collision operator, and there is that extra term, which is also the absorption due to the hole, and that involves that function phi of t, which is the limiting distribution of exit times or mean free path. The limiting distribution of free path length. And so this function is a very nice differentiable function, and what you have here is phi prime over phi, which is negative, but expressed at the infimum of s and t times f, right? So that is the equation. And now, because if you look at this transport equation here, s equals 0, the field is incoming, so you have to prescribe a condition for s equals 0. So the condition is the gain term of the original linear collision operator. So it involves sigma times the integral from 0 to infinity times f, ts, x, and v, but you let the integral gain term acting on capital F. And as an initial condition for t equals 0, you prescribe the initial data for f epsilon, so it's f initial of x and v, and you need to add the dependence in the extra variable s, and you do that by imposing, for instance, sigma e to the minus sigma s. So it's you multiply this by your favorite probability distribution in S. Okay, I will come back to this choice in a minute, right? Now, the first observation is that, unlike in the case of the periodic homogenization problem for the Laplace equation, if you homogenize the linear Boltzmann equation in a periodic system of holes, then you need, to describe the limiting dynamics, you need an additional variable S. Additional with respect to the usual variables t, time, x, and v of the kinetic theory of gases. So in other words, in the end, right, the phase space for that equation that I wrote for you, it's the space, it's the plane times the velocities. That's the usual phase space of kinetic theory, positions and velocities. But here you add an extra piece in that phase space, which is the half line where the extra variable s lives, right? So there's a change of phase space. Now, for the physical interpretation of S, so the fact is that if you look at the probabilistic interpretation of the linear Boltzmann equation, well, you can do that with a jump process in velocity. Particles change velocities discontinuously at exponentially distributed time. The parameter of that exponential clock is sigma in that equation. And now the variable s in the model is the time since the last jump in velocity due to the collision process of the Boltzmann equation. And you need to record that the age of the velocity, the age of the current velocity, in order to be able to measure the interaction of the jump process with the absorption by the holes, right? So this is essentially the physical interpretation of this S in that function, that limiting function capital F. So in other words, you can summarize the result above with the following diagram. You start with an F epsilon, which is the number density in the usual phase space. By some procedure, which I'm going to explain in a minute, you lift it to the extended phase space, even with epsilon. So this capital F epsilon obeys an equation which looks like a linear Boltzmann equation. You homogenize the equation governing the capital F, you get a limiting F, and then you recover the limit of the little f epsilon by integrating out the extra variable s, right? So that's the procedure to prove that theorem. But before I explain how the proof works, let me go back to question number 2, which is to find the asymptotic behavior of the mass. So because of the holes, particles will disappear, you lose mass in the system, and it would be nice to know how you do that. Okay, so the second result, if you want, which is a consequence of the first, is that in the limit, as epsilon tends to 0, the total mass of the particle system converges to a function m of t, which again I will describe by means of a little m that depends on the same extra variable s, right? So that m of t, capital M of t, total mass of the system at time t, will be an integral in s of little m of t and s, and that little m of t and s is the solution of this PDE here. So you have dtm plus dsm plus b of t and s times m equals 0, t and s positive, where b of t and s is this absorption rate here. So there is the absorption rate sigma that comes from the original loss term in the Boltzmann collision operator, linear Boltzmann collision operator. And there is the second absorption rate, which is minus phi prime over phi at s inf t, which comes from the geometry of the perforated domain, right? Again, you prescribe a boundary condition for s equals 0 because it's incoming. It's a transport equation, the simplest of transport equations here. So you prescribe m at t s equals 0 is sigma times the integral from 0 to infinity of m t and s ds. And you prescribe initial data for t equals 0. And for the choice of initial distribution, initial profile in S, which I showed you before, you have this exponential distribution in S times the initial mass, capital M of 0, right? So the initial mass is the total integral of F initial. Now, once you have the solution, so this type of PDE goes by the name of renewal equation, and it's called this way in the book by Pertam on transport equation and in biology. Whereas renewal equations usually refer to integral equations classically, but you can reduce that equation to an integral equation, and I will use that in a minute. Okay, anyway, so the total mass for that system obeys a renewal PDE. So that's the second result. And now in the long time limit, what happens is that the total mass, the total number of particles, decays exponentially fast, right? And here's what happens. For each collision frequency sigma, there is a unique exponent, c sigma, which is between minus sigma and 0, such that as t tends to infinity, the mass is actually equivalent. What happens is that the solution the m of t, which is computed as the integral in S, the solution of that equation, right? So you've already passed through the limit in epsilon. So that thing behaves like a constant times e to the t times c sigma, as t tends to infinity, and the constant is the total mass initially divided by this integral here, right, which is a function of sigma. I remind you that phi of S is the distribution of exit time in the vanishing epsilon limit. And now if you let sigma go to 0, if you diminish the collision clock, or the collision frequency, then c sigma is equivalent to minus sigma, right? So it vanishes. And it converges to a constant in the high, in the very collisional case. When sigma goes to infinity, the collision frequency goes to infinity. It's like a diffusion limit, and in that case, c sigma tends to 2, right? No, I can do that with the remote. All right. So now, why did I ask the question of the asymptotic behavior of the mass? As a matter of fact, this asymptotic behavior, this exponential convergence here, it's not uniform as sigma tends to 0. As you can see here, as sigma tends to 0, essentially c sigma is equivalent to minus sigma, so it converges to 0. So you lose the exponential decay here, and besides, but this goes to plus infinity. So in fact, what happens is that for sigma equals 0, for the free transport case, the mass loss rate is not exponential at all. So it's given by the following asymptotic behavior of the function phi itself, of the distribution of exit times. So you can, because it's there is no collision process, you can integrate along characteristics, you can find the solution explicitly, and what you find is that the total mass at time t is my limiting distribution of exit times phi of t times 1 over 2 pi, the integral of the initial, well, I mean times the initial mass, right, times m of 0. And, oopla, since you know explicitly this phi of t here, it's not hard to find that as t tends to infinity, the m of t is equivalent to the initial mass divided by pi squared t. Right, so the phi of t is equivalent to 1 over pi squared t. So you have a very slow decay of the mass as time goes to infinity in the non-collisional case. As soon as you switch on the collisions, the thing becomes exponential, right? The mass decay rate becomes exponential. So the fact that phi of t is equivalent to 1 over pi squared t was the precise constant 1 over pi squared. I mean, to do this, I think you need to be in space dimension 2. But what was known before is that in any case, this phi of t here cannot decay exponentially fast even in higher dimensions. In any space dimension, phi of t will possibly oscillate between two profiles like constant over t, right? So you don't find exponential decay even in higher dimensions. So it's not an artifact of space dimension 2. But the problem is that this function phi of t is extremely hard to analyze in space dimension higher than 2, right? Because it has to do with simultaneous rational approximation. This is tricky business. Okay, so what happens in the collisionless case is this, right? So in the collisionless case, you look at the free transport equation in the perforated domain with the absorption boundary condition. Anytime a particle meets an absorber or a hole, it disappears, so you have no particles leaving the surface of the holes. And f epsilon at t equals 0 is these f initial. And what you can prove is that for each t, f epsilon converges, well, I mean, you have to take Cesaro average on the obstacle radius. Okay, so it converges to, in that sense, to an f of t, x, and v, almost everywhere in x and v. It's not a weak convergence. It's almost everywhere, right? Because it's an ergodic theorem of some sort. And that f is the solution of d by dt plus v del x f equals to phi prime over phi of t, f of t, x, and v, with the initial data f in. And here, as t tends to infinity in that thing, you find that this is equivalent to minus 1 over t. Now, so you observe that for this problem, you lose the exponential decay of the mass, but for this system, you don't need any extra variable to describe the limit, right? The limiting density here satisfies itself an equation of the same type as the original free transfer equation. So it's very much like in the diffusion case, except the only thing that changes is the limiting equation is non-autonomous, because you have this rate that depends on the time, right? But it's not exponential, what can I say? So it can be autonomous. So the need for the extended phase space with this additional variable s arises only if you have the periodic distribution of holes, the periodic distribution of absorbers, and the positive collision frequency, right? So you need both in order to have these extended phase space phenomena. All right, so having described the results, let me give a few ideas in the proof. Actually, the proof is not extremely hard. There are similar instances where homogenization will require having extended phase spaces, especially the Boltzmann grad limit of Laurent's gas. But this is a much trickier result. So, in fact, you can think of this result here as an example where you can observe this behavior of homogenization with an extra variable that comes out naturally, and it's an example where you can do the computation at minimal cost if you want. Okay, so if you remember what I told you before, the idea was to start from the original linear Boltzmann equation and to lift the particle density already before passing to the limit. You want to lift the particle density to the extended phase space, right? So you start from the f epsilon of t, x, and v in the standard usual phase space. So this is your Boltzmann equation, right? This is the linear Boltzmann equation. This is the boundary condition. This is the initial condition. And what I'm saying is that even for a fixed epsilon, this is equivalent to saying that f epsilon is equal to the integral of capital F epsilon t s x and v ds. So you introduce the extra variable before passing to the limit, where that capital F epsilon is a solution of the lifted Boltzmann equation. So, you know, I mean, you have dt f epsilon plus v del x f epsilon plus ds f epsilon plus sigma f epsilon equals 0. So here you have the usual absorption, the usual loss term in the collision operator. Here you have the term, I mean, this ds f epsilon will produce the gain term, will correspond to the gain term, because for s equals 0, well, I mean, the field is incoming. For s equals 0, you prescribe f epsilon to be equal to sigma times the integral in s of the gain term, the collision operator. You prescribe f epsilon to be equal to 0 on the boundary of the holes for outgoing particles. And you prescribe f epsilon to be the initial data, little f in of x and v, right? So that same function here, except that you need to add dependence in the extra variable s, and you do that by putting any probability density which you like on the half line. For instance, you could take pi of s equals to sigma e to the minus sigma s. But you don't have to, because what happens is, like, as you can see, if you take that problem here and you average out the s variable, you will find rather easily that it's you find this problem. It's essentially, it's almost obvious, right? So whatever pi is, you find the same problem after averaging. So the capital F epsilon itself may depend, I mean, will depend in general on the specific choice of pi, but of course not the little f epsilon. It's a solution of the same linear Boltzmann equation always. So for instance, you can pick this problem here, which corresponds to saying that the age of the velocities at time 0 are exponentially distributed. So it's like you have a standard linear Boltzmann dynamics operating, and at time equals 0, you suddenly open the holes. Suddenly the particles, oops, might fall into the holes. That's the meaning of that choice here. Okay, so now step 2, you take that problem here and you solve for f epsilon by the method of characteristics. And if you do that, then you have two pieces in the solution, right? Because you have the piece where when you go back on characteristics, you're going to hit first that boundary condition or that one, depending on whether S is smaller than t or larger than t. Okay, so when S is smaller than t, what you hit first is the boundary that produces the gain term of the collision operator, right? So you have this term here. And for the other part, which corresponds to t being smaller than S, what you hit first is the boundary condition t equals 0. It's the initial condition t equals 0. Okay, so here you already see that there's going to be no problem with that term here, because that term, everything is fixed except for that indicator that epsilon, tau epsilon of x over epsilon and v is larger than t, and that we said converges weakly to phi of t. So this one is no problem. This one is easy. So the difficulty is going to pass to the limit in that term here, because it involves the product of a solution f epsilon, which has oscillations in it because of the holes, and the tau epsilon, which carries the distribution of holes, which depends on the distribution of holes, and some correlations may appear in that product. We're going to see that, right? All right, so now you extend f epsilon and little f epsilon by 0 inside the holes. You call f epsilon between curly brackets, and likewise with the small f epsilon, the extended densities. You extend by 0 inside the holes. And it's very clear that when you pass the limit in the second term, what happens is that you keep everything here. You keep that function here, and you pass to the limit into that term here, and that term produces a capital phi of t. So passing to the limit in the second term is easy and gets you this. Now, for the first term, you observe that, well, the first term you have to pass to the limit into this product, and actually the k operates on the little f and not the capital F, because you averaged out the s variable. Okay. Now, these f epsilon, the little f epsilon, when you extend it by 0 inside the holes, it satisfies an equation like this. So you have d by dt plus v del x f epsilon extended by 0 inside the holes, which is equal to the boundary term. So you have f epsilon times v dot nx on the boundary of the holes, well, plus actually the collision term, which I forgot. But a collision term is a nice term. It's a 0-order term. It's continuous, acting on f epsilon, no problem with it. So this one involves a measure, which is concentrated on the boundary of the holes. And what happens is that this f epsilon is bounded uniformly in epsilon by the maximum principle. And you have the d by dt plus v del x f epsilon is order 1 in the space of measures. And then by velocity averaging, you conclude that k f epsilon between curly brackets is strongly relatively compact in LP log for each p larger than 1 less than infinity. Observe that the fact that this guy is order 1, this is another way of saying that the holes are precisely at the critical size, right? If the holes would be bigger, then the measure of the surface of the holes would make this term unbounded, right? So the fact that it's equivalent, that it's order 1, is precisely the fact that you're a critical size, right? Okay, so then, well, you conclude that you have a product here. Well, this term converges weakly. This term converges strongly by velocity averaging. You can pass to the limit, and you end up with this limit here. And when you patch everything together, well, I mean, when you patch this piece of the solution and this piece together, you find that it's a solution of the homogenized equation. So you found the solution before finding the equation. It's not very nice, but that's kind of usual in this business. Now, for the distribution of the mass, well, I mean, the equation for M is obtained by integrating out the x and v variables in the homogenized equation. So M of t and s is equal to this integral in x and v of capital F. And you check, again, by the method of characteristics, that since that M solves the renewal PDE, then when you integrate out the s variable, well, the capital M of t satisfies the renewal integral equation written here. So the kernel is sigma e to the minus sigma s times phi of s, right? So of course, this kernel, when you integrate it, you find something which is less than 1. It's because you lose mass. It's natural. And then you only have to apply the classical results on the asymptotic behavior of integral equations for renewal type, which you can look up in the book by Feller, to find that M of t is equivalent to a constant times e to the xi sigma t as t tends to infinity. And xi is defined as the only solution of Laplace transform of phi of t equals 1 over sigma. And if you study that equation, you'll see that there is only one exponent between minus sigma and 0. So it's fairly standard. Okay, so this is the answer to both questions which I raised at the beginning. Maybe some amplifications, open questions, or possibilities of extension of that result. So okay, so while the asymptotic behavior of the total mass is the first obvious question in connection with that problem, because we've seen that if you don't have the collisions, the mass decays extrabarically fast but not exponentially fast. If you switch on the collision, then it decays exponentially fast in a way that is not uniform in the collision frequency. Okay, but it will be nice to understand the limiting behavior in time of the solution of the homogenized equation itself. So if you think of that capital F as the analog of a solution of linear Boltzmann equation, well, for a linear Boltzmann equation in a torus, say, the asymptotic behavior is fairly clear because you have spectral gap and everything is known. So is there anything like that here? Well, good question. Well, it's a question at least. So for instance, you assume that the initial data is periodic with period 1 in the space variables, and that the epsilon, the small parameter epsilon, is 1 over n. So really you have a box, and you partition that box into smaller boxes, and inside you have the holes, right? That's the, you look at this particular case of epsilon small parameter. So a natural question is whether there exists an alpha mass loss rate and a profile which depends on x, x, and v, so that the leading order term in the long time limit of f epsilon will be e to the alpha t times psi of s, x, and v. If you seek psi as independent of x, then you plug that expression into the homogenized equation, you let t go to infinity, and you pick up that equation here to be satisfied by psi with this boundary condition for s equals 0. And well, you can solve it essentially explicitly. You find that psi of s and v is in fact psi of v times e to the minus sigma minus alpha s phi of s because of that equation here. And when you use the boundary condition, then you have this condition that comes out here. And an obvious solution is to take k psi equals psi, meaning that psi is going to be a constant, and 1 equals to this, which is precisely the defining equation for xi sigma instead of screwed up. I mean, here it should be alpha equals, no, it's all right. So with alpha equals xi sigma being the unique solution of that equation here. Okay, so in other words, is it true that as t tends to infinity, the solution of the equation, the homogenized equation, converges to this profile here, right, where psi is a constant, which is given by the same constant as you would get when you homogenized the standard linear Boltzmann equation, that is the total mass, right? Is it true that you have this? So seems to be a natural question. That would obviously entail the by integrating out the extra variables, that would imply the asymptotic behavior of the mass. Okay, that's if you want you've distinguished, you've conditioned the mass by extra variables here. But the problem is that it's not completely clear at the moment that psi is the only possible, that particular solution is the only possible one. So there is a uniqueness problem here, which I think is probably not too hard. Is it true that the solution F converges to that profile, which is the same question as I raised? And in some sense to be made precise as time goes to infinity. If so, what is the convergence rate? Is it really exponential, et cetera, et cetera? And is there a Lyapunov functional for the homogenized problem? I mean, probably yes, and probably you can find the answer to that question by working on the ideas that you find in the book by Pertam. Anyway, so there are several open questions which are probably not too hard in connection with that problem. Now, let me remind you that for a random Poisson distribution of scatterers, then phi of sigma will be an exponential, and all the questions above, they correspond to the spectral gap property for the linear Boltzmann equation and the torus, so it's fairly standard. So that will be the extension of that standard property to the homogenization, to the homogenized model with the extra variable. Okay, so, well, I mean, the conclusion is that the homogenization of a linear Boltzmann equation with absorption by a periodic system of holes requires using an extended phase space to write the homogenization equation. And the homogenized distribution function is obtained by averaging out the extra variable, but it doesn't seem to satisfy itself a closed equation, closed integral differential equation without delay term, right? I mean, if you want to have a Markov process, you really need to add these extra variables. And you observe exponential decay of the mass in the long time limit as a consequence of the renewal structure of the limiting equation for the mass. And, well, I mean, last question is whether one can use this idea of working on an extended phase space for other singular asymptotic homogenization problem, other singular asymptotic regimes. That's perhaps interesting, I don't know. This is an open question. Thank you for your attention.
You. So there are some questions. Yep.
Is it a surprise that the limiting equation is rotationally symmetric? Because you start with.
Well, I'm not sure. I'm not sure it's true if you have a collision operator, collision which is not isotropic. I don't think it's true. Now, if it's isotropic scattering, yeah, I mean, if it's isotropic scattering, I mean, you observe that all the time. For instance, for the Boltzmann grad limit of the Lorentz gas, even though at the microscopic level you have a lattice, if you have a regular lattice, when you pass to the limit, you get something which is isotropic. Yes.
But the limit without scattering wasn't that isotropic too?
yes, because you see okay. The thing is, the thing is, I guess. Okay, so let me go back to this. All right, so you have this result here. The phi of t is the limiting probability that tau epsilon be larger than t. The fact is that it is true also if you condition by v, right? So, in fact, another way of saying this, if you want more analytical way of saying this, is that this limit here can be made pointwise in v, right? Pointwise in v, but you have to take Cesaro average if you want to observe it pointwise in v. So in other words, what is very, I mean, the interaction of the particle path with the structure of the lattice somehow disappears here. It's true that the tau epsilon is extremely irregular depending on the velocity. But in the limit, even pointwise in v, when you average in the obstacle radius, this is the same limit, right? So that's the result of a computation. It's not an obvious fact, but it's true. So then I suppose that this, after all, if the anisotropy of the lattice disappears at this point, this is probably the strongest. I mean, this is probably the most obvious place where it's involved. It's not a surprise in the end. You don't see it at all in the equation.
Okay, other questions or remarks? Yep, Pierre?
If you do the diffusion approximation, can you connect with the constant that was found by Murat and Ionescu?
Yeah, I mean, that problem of doing the diffusion approximation of the homogenized equation, what it gives you is you get a constant, of course. And the constant that you get involves the derivative of this guy at t equals 0, right? So I don't know if you can say that this has anything to do with the capacity. You know, I mean, the interpretation of the constant in Ionescu-Murat is the capacity of the sphere. So here it's a different business. But yes, you find a constant. The constant is the derivative of phi at time t equals 0. Yes, that's true.
Yo. Other comments, questions? Seems not to be the case. Then, yeah, let's thank you again.